Hello students, welcome back to A-Star Tuition channel. Today we'll continue our discussion about dynamics part 3. Particularly we will discuss about momentum, impulse and the conservation of momentum. Let's start. Now, momentum or linear momentum of an object is associated with a quantity when an object is moving. Now, when an object has a mass of m and it moves with a velocity v in certain direction, then we say that the momentum or the linear momentum of that object is equal to simply mass times the velocity factor. So this is quite simple. Now let's look at the unit involved. Okay, so mass has a unit of kilogram and velocity has a unit of meter per second. So momentum has a unit of kilogram meter per second. Yeah, so let me illustrate with something simple. An object moves, let's say the mass is 3 kilogram, right? And then it moves in one direction with velocity in which the speed is equal to 5 meters per second. Now if I multiply the mass with the speed with the velocity, then the momentum, the magnitude of the momentum is equal to 3 times 5 equal to 15 kilogram meter per second. And we can also mention the direction. Remember, momentum is a vector because although mass is scalar, velocity is a vector. So you can see that the momentum factor and velocity factor are parallel. Yeah. So if velocity is going to one direction, then momentum is also going to the same direction. So the only the constant of proportionality is the mass. Okay, so this is momentum. A quantity that is also equally important is what we call as impulse or change in momentum. So imagine that particle is moving with certain direction, with certain velocity, and then suddenly the velocity changes, whether the direction changes or the speed changes. So in that case, there is a quantity associated with that, that is what we call as the change in momentum or impulse. Okay, so impulse or change in momentum. Now, so then from the term that we use here, it is obvious that we can find change in momentum by subtracting the final momentum with the initial momentum. Now remember, this is a factor subtraction. Yeah? So you cannot just subtract the magnitude. It doesn't work that way. Let me give you an example. The first example is when the velocity, the magnitude of the velocity changes. Yeah, the speed changes. So the mass here is again 3 kilogram. It moved with initial velocity and the magnitude is 5 meters per second. And then some time later, the same mass now move with the same velocity, the different velocity, but same direction, by the way. So the speed is now, let's say, 7 meters per second. So in this case, it is quite easy to see that because the direction doesn't change. So you subtract the final factor, which is, this, pi, subtract with pf, subtract with pi. Now remember, pf has the same direction as pf and pi has the same direction as pi. So in this case, you just have like this is pf and then minus pi. This is minus pi. So then the result is this. So this factor here is delta p, pf minus pi. Now in this case, it's easy to see that the magnitude is simply equal to the final minus initial. Remember, the initial has a magnitude of 3 times 5. That's 15 kilogram meter per second, and the final has a magnitude of 3 times 7 equal to 21 kilogram meter per second. So therefore, we can say that delta P is 21 minus 15 equal to 6 kilogram meter per second, and we also mentioned the direction, to the right. Remember, delta P here, or impulse, the symbol used is usually I, vector I, is a vector. So therefore, you need to understand not only the magnitude but also the direction. The next example that you will see is, what if the velocity changed its direction while the speed doesn't change? Take a look at this example. Now this is again the same, an object with the mass of, let's say again 3 kilogram. It's moving to the left, so it has an initial velocity to the left with the magnitude or the speed equal to 5 meter per second, right? So then here the object will hit a wall, a firm wall, so that the object after hitting the wall, it will rebound. Now when it rebounds, the velocity is different from before, because you can see that it's going to the left initially, but now it's going to the right. But then the speed or the magnitude of the velocity remains the same, which is equal to 5 meter per second. Now, some common mistake encountered in this situation is that, let's look at the magnitude of the momentum. The magnitude of the initial momentum is equal to 3 times 5. So it's going to give you 15 kilogram meter per second. And then let's look at the final momentum, which is 3 times 5 equal to 15 kilogram meter per second. So you can see that the magnitude of the momentum doesn't change, right? So then some common mistake that encountered by students when they learn momentum for the first time is that they subtract the final magnitude of momentum with the initial magnitude momentum, and they say, okay, the change in momentum is equal to 0. Now this is a common mistake. So that's not the answer. So it's not 0. Well, in this case, delta P, magnitude of delta P is 0, but delta P, this is actually delta P itself, the magnitude of delta P is not 0. That means what is 0 is PF minus PI. Now this is 0, but then the change in momentum itself is actually non-zero. Why is that? Because remember, change in momentum is a vector. You can't just subtract the magnitude right away like that. What you need to do is, you need to do factor subtraction like usual. Okay, so in this case, the final momentum is in the same direction as PF, so it's going this way. So this is PF, so let's just say that since momentum is in the same direction as velocity, so PF is drawn like this. Now, but what about PI? PI is going this way, but remember, this is not PI, this is negative PI. So PF plus negative PI, so since PI is going this way to the left, so negative PI would be to the right. So this is negative PI this way. So this is negative PI. So then when you add these two factors, PF plus negative PI, it gives you a factor that is actually twice as long as the initial. Well, that's because both PF and P minus PI have the same magnitude. They both have the same magnitude. Okay, so you can see that this is PF minus PI. Now, as you can see, delta P itself here is not 0. It's not 15 minus 15. So in fact, it's actually equal to 30 because this is 15. Remember, this is 15, this is 15, so then the magnitude of the change, yeah, is equal to 30 kilogram meter per second. Now the way we work it out is we can actually do it like by assigning a negative sign to negative velocity. Now usually moving to the left is negative, moving to the right is positive. But remember, it's just a convention. If you use that convention, as long as if you use different convention, as long as you are consistent, then that should be okay. Now, so in this case, I would say that BF minus BI, if you want to do it, short way, you can just say, okay, M phi final minus M phi initial. So it's equal to M times phi final minus phi initial. So then without, this is actually a factor, but we can just use the, the magnitude. So this is like what, 3, 5 minus 5, and then say to the right. So the answer is going to be just like before, 30 kilogram meter per second to the right. Yeah, so I hope you pay attention to this case, yeah, where the change in momentum, it cannot be zero just because the magnitude doesn't change. We have to be looking at the direction, yeah, because remember, this is a factor addition, or in this case a factor subtraction. Next, we want to discuss about what causes change in momentum. Now remember, momentum, as I discussed before, it's the product of mass and velocity. Now in most cases, mass stays constant. It doesn't have to be the case. There are actually some cases in which the mass actually changes while the velocity is constant. But regardless, I want you to think about what happens when the velocity changes while the mass is constant. What caused the change in velocity? What is change in velocity? Now in the previous video, in I think the first part of the video about dynamics, we learned that acceleration is equal to rate of change of velocity. So let me write down, acceleration equal to the final velocity minus initial over time, delta t. Now remember, we also mentioned that according to Newton's second law, acceleration here, if I multiply by mass, that gives you resultant force. So resultant force equal to mass times acceleration. So if I multiply mass here, M phi final minus phi initial over delta t. So you can see that resultant force actually causes the change in momentum. Now if I were to multiply, this is going to give you phi M times phi final minus M times phi initial over delta t. M times phi final, that's equal to final momentum, and M times phi is equal to initial momentum. Yeah, so this actually equal to delta p, change in momentum over delta t, or equal to impulse over delta t. So as you can see, this is Newton's second law, but now it's written in a more general equation. Remember, we mentioned that when the mass is constant, resultant force equal to mass times acceleration. However, even when the mass is not constant, Newton's second law is still valid. But in that case, we need to take into consideration that maybe mass is also constant. Maybe mass is not constant. So it's actually it's actually more general to write Newton's second law in terms of change in momentum. So let me state it here. Yeah. So the change, the modification to Newton's second law. Yeah. We can write it as resultant force or rate, resultant force acting on an object is equal to the rate of change of momentum of that object. Now, if you write it this way, then whether the mass is constant or not, this is still true. Now, in fact, let me bring a bit of calculus here. So if you're not familiar with calculus or differentiation, then maybe it's okay to skip this part. But then if you have like some knowledge about how to differentiate using product rule, then you can see that here I can write it as phi dm dt delta m delta t plus m dv dt. Now dv delta phi, delta phi delta t. Now this part is the acceleration. The acceleration part is this, delta v delta t. But then this is associated with the change in mass. Yeah, so a system in which the mass increase or decrease, like rocket motion. Now remember that a rocket, is a body of aircraft that is used to launch to outer space. When the fuel is burned through combustion, then the residue will be expelled from that. So that actually caused the mass of the entire rocket to decrease, and it actually contribute to the change in momentum. Hence, there's a force associated with that. Now, we can also calculate the amount of change in momentum or impulse by using the graph of force function time. Okay, so let's say this is the magnitude of the force function time. So the area under the graph of this, from, let's say, from 0 to certain time is equal to the impulse. So you can find impulse by equal to impulse or delta p, magnitude of delta p. Magnitude of impulse, magnitude of delta p, that's equal to the area under force time graph. Now, if the average force is given, then you can calculate the impulse by average force. This is average value. Average force times delta t. So impulse can also be calculated by using the value of average force, the magnitude of average force multiplied by the time. The time as in how long it takes for the velocity to change from a certain momentum value to the next momentum value. Now let's talk about the unit for impulse. Since impulse is change in momentum, so it only makes sense if the unit for impulse is also equal to the unit for momentum. Because remember, the change in the quantity means that how much the quantity has changed. So then it should have the same unit as the quantity itself. Now, indeed, that's the case. So remember, the momentum has a unit of what? Momentum has a unit of P equal to mv. So m times v. The formula is mv, but the unit is kilogram meter per second. So change in momentum is also that. However, if you look at this formula, this suggests that you can also write the momentum as Newton times second. Now, Newton second is a unit that we normally use for impulse. But please bear in your mind that this is equivalent to that. So I can show it to you. Remember, Newton is in kilogram meter per second square. And then multiplied by a second, you get what? Kilogram meter per second. So this is exactly equivalent to momentum itself. Now, let's discuss about what caused the change in momentum. Now, remember, momentum, as we discussed, it's P equal to mass times velocity. So the change in momentum would be mass times v final minus v initial, like that. Okay? Now, here we assume that the mass is constant. But you know what? We can actually don't assume that. So it's P final minus P initial. Now remember that momentum is proportional to velocity. Yeah, so it's parallel. So velocity and momentum are two factors that are parallel to each other. So when we talk about change in momentum, normally we also discuss about the change in velocity. Now in the previous video, we talked about acceleration being the rate of change of velocity. So in fact, this is the average velocity, average acceleration, P final minus P initial over time. Now, let's multiply this by m and what happened. See what happens. So m times a equal to m P final minus P initial over time. Now, when you multiply mass with acceleration, that is according to Newton's second law, resultant force. So the resultant force is equal to mass times P final minus P initial over time. So if we were to distribute this over, you get m P final minus m P initial over time. So this is P final minus P initial over time, or delta P over, let's call this delta T, change in time, over delta T. So as you can see that in the Newton's law video, we discussed that resultant force is mass times acceleration. However, this is actually more general. So let's write down the modification to Newton's second law. Okay, so now we write down sigma F resultant force as delta P over delta T. Now, from this point, I want to derive something using product rule of differential calculus. So if you're not familiar with that, you can read about that, but it's actually not that difficult. So the idea is that if you have mass times velocity over delta T, then according to chain rule, this will give you m dv dt plus p dm dt. So there are two terms in which one of the term is something that you're familiar with. That's equal to mass times the acceleration. Delta V delta T is the acceleration. So this is the term that is caused by the change in velocity. However, there's a term that is now appear in the equation that wasn't here before. Now this term relates to the change in the mass. So in the Newton's second law that we originally discussed in the the first video, we always assume that the mass is constant. Now, but when the mass is not constant, there's still resultant force associated with that. Now, this is actually apparent in a system in which the mass is not constant during the motion. Like for instance, the motion of a rocket. Remember, when when a rocket is actually launched into space, some of the fuel is burned and the residue for the combustion is expelled from the system, hence causing the change in the mass. So it also contributes to the resultant force on the system. Next, we will learn about how to calculate the change in momentum or impulse. Now, if the magnitude of average force during which momentum changes is known, in other words, F average, the magnitude is given, you multiply by how long the momentum changes from one value to a new value, then the magnitude of impulse is simply the magnitude of the average. So this is the magnitude of average force acting on the object while the momentum changes. So while the momentum is changing, so delta t is simply the time in which this process of changing momentum occurs. Now, this is one way, but then another way is if, for instance, if the force function time graph is given, the magnitude force function time is given, then if you want to calculate what is the impulse or the change in momentum of the system during this time span from 0 to t, all you need to do is to calculate the area under the graph. So then impulse can also impulse the magnitude, that is, and the magnitude of impulse can be calculated by the area under the FP graph. Now please understand, when this is given the magnitude of the force function time, so when the force itself is negative, usually negative because the direction changes, you need to account for the fact that it changes direction, the force changes direction. What I mean to say is this: let's say instead of magnitude of the force, you have like the force. Remember, this is one-dimensional motion, so you know that force negative means that it's the other direction, the opposite direction. So if you have something like this, then the magnitude of impulse is simply area 1 minus area 2. So magnitude of impulse is whatever the area, calculate the area of this shape minus the area of the shape below the t-axis. So please understand this, because this is very important. You cannot just add the two areas together, because this force being negative actually contributes negative change in momentum. So that's why you need to use minus sign here. Okay, now what about the unit? Now impulse is the change in momentum. So because this is a change in momentum, so therefore the unit for impulse should be also the same as the unit for momentum itself, which is kilogram meter per second. Remember, momentum has unit kilogram meter per second. So indeed, impulse has the same unit as change in momentum. However, when you look at this formula, this suggests that you can also use the unit for force and time to calculate the unit for impulse, which is Newton times second. Okay, but then remember, Newton second and this actually they're equivalent. So how to see that they're equivalent? Well, Newton is the unit for force. That's just mass times acceleration. So kilogram meter per second square times s. So it's going to give you kilogram meter per second, which is the same as this. Next, we'll discuss about the idea of conservation of momentum. Now, remember that earlier I wrote resultant force equal to rate of change of momentum. So whenever momentum changes, then there's force associated with that change in momentum. But what if the resultant force is 0? Now, when I say resultant, I mean the external resultant force. So external resultant force, when it's equal to 0, that means the rate of change momentum is 0, which means that the change in momentum is 0, which means that the final is equal to the initial. So the momentum, the final momentum is equal to initial momentum. Now this can only happen if the resultant external force on a system is 0. Now when you have a system of only one particle, and the one particle, let's say that, okay, let's look at this situation. So this is one particle with mass 1 moving with velocity v1 and another particle m2 moving with velocity v2. Now when they collide, what happens is that there will be forces acting upon them, so that the first particle will exert a force on the second particle, and according to Newton's third law of motion, the second particle will also exert the same force to the first particle in the opposite direction but equal magnitude. Yeah. Now, in this case, even though each individual particle experienced change in momentum, but then there is no external force acting. There are internal forces. The one that I mentioned earlier, when they collide, they each will experience forces. Yeah? And these forces are internal to the system if we regard this as the system. So therefore, when the system itself has no resultant external force, or in other words, the resultant external force is 0, then the momentum of the system is conserved. Now, I want to explain how conservation of linear momentum is associated with Newton's third law of motion. So here we see that the momentum of the system before collision, m1 v1 plus m2 v2, right? Now later, the momentum of the system is m1 v1 prime plus m2 v2 prime. Yeah, so let's say that now after the collision, this is v1 prime, m2, this is v2 prime. Now, because there are no external forces acting on the system, then the momentum of the system initially, which is before the collision, equal to the momentum of the system after collision. So we put an equal sign here. Now, let's do some algebra here. So I'm gonna move v2, m2 v2 to the left hand side. I'm gonna move m1 v1 to the right hand side, and I wind up with m2 v2 prime minus plus m2 v2 equals m1 v1 minus m1 v1 prime minus m1 v1. So this is m1 v1 prime minus v1. Remember, the prime quantity the prime quantities are associated with the velocities after collision. Yeah, so here this is minus m2 v2 prime minus v2. So this is the change in the velocity for the second mass, and this is change velocity for the first mass. Yeah. Now if I multiply with 1 over delta t on both sides, so this will give you what? It will give you the acceleration. So this is the acceleration for the second mass, and this is the acceleration for the first mass. So this is the force acting on the second mass, and this is the force acting on the first mass. Now this is the statement of Newton's third law of motion. So for every action, there's equal and opposite reaction. So in this case, the first mass hits the second mass and exert a force in a certain direction. In this case, the direction is to the right, and the reaction is the second mass will exert the same force, same magnitude, force with the same magnitude in the opposite direction, F2. So you can see that this indicates that these collision forces between the two particles or the two objects are equal in magnitude but opposite in direction. Last, we want to discuss about type of collision. Now earlier you saw an example about two objects collide with each other. Now, in most physics problem in high school, when you have two collisions, we usually assume that the momentum is conserved. And the reason is because during collision, there is no external force to the system. So even though each individual momentum changes, as a system, the total momentum is conserved, as we mentioned about that previously. So, but the thing is that this change in momentum equal to 0 of the system, so P final equal to P initial, this condition is actually not enough, is not enough or insufficient in general to determine what happened next after collision. What is the velocity of each after collision? Now, in order to know what happened next, it depends on the type of collision. Now, there are actually two types of collision. First is the elastic collision, and the second is called inelastic collision. Now, for the inelastic collision, actually we can also divide into two different types. This is like inelastic but still partially elastic. So it's inelastic but it's partially elastic. And the second one is completely or perfectly inelastic. Now again, inelastic means it could be partially elastic or perfectly inelastic. Now for elastic collision, what you need to know is that the kinetic energy of the system is conserved, so that we can say the change in kinetic energy of the system is 0. Now for perfectly inelastic is that when the two objects collides, after the collision they will move together or they will stick to each other. So move together or stick together with the same velocity. Now for the partially elastic, obviously there is a change in kinetic energy. Usually the change in kinetic energy is negative, so the kinetic energy decreases that. For the perfectly inelastic also, so in this case the change in the kinetic energy is non-zero, is less than 0. Yeah? So because the kinetic energy decreases. Now let's look at the example for elastic collision. Suppose that you have mass 1 equal to 3 kg. It moves with velocity or speed equal to 5 meters per second. And then mass 2 is equal to 2 kg. And it moves with velocity 2 meters per second. Now we can say that the initial momentum of the system is m1 v1 plus m2 v2. That's equal to 3 times 5 plus 2 times 2. That gives you 19 kg meter per second. Okay. Now after collision, we can say that the momentum of the system is, let's say this is v1 prime and this is v2 prime, yeah, m2 m1. So m1 v1 prime plus m2 v2 prime, this gives you 3 times v1 prime plus 5 times, actually this is m1 is 3, yeah. So yeah, 3 v1 prime plus 2 v2 prime. So then by setting the initial momentum of the system with the final momentum of the system, you get 19 equal to 3 v1 prime plus 2 v2 prime. Now you can see that this is an equation with two unknowns, v1 prime and v2 prime, and this condition, which is the conservation of momentum in itself, is insufficient to determine what happened next. What is v1 prime, v2 prime? Now if we know that the momentum is, the collision is elastic, then we can actually add the third condition and the second condition, which is there is no change in the kinetic energy of the system. So what is the kinetic energy of the system initially? So it's equal to half m1 v1 square plus half m2 v2 square. So it's equal to half times 3 times 5 square plus half times 2 times 2 square. So this gives you 75 over 2 plus 8 over 2. So this is equal to 83 over 2 joule. Yeah, remember energy is in joule. Now, if the collision is elastic, then the kinetic final should be equal to 83 over 2 as well. What is the expression? Half m1 v1 prime square plus half m2 v2 prime square. So this is equal to half times 3 times v1 prime square plus half times 2 times v2 prime square. So this is equal to 3 v1 square, v1 prime square plus 2 v2 prime square over 4. Actually over 2, yeah. So, and then we can set this expression, the final kinetic energy, the initial kinetic energy, which is 83 over 2. So then in this case, 83 equal to 3 v1 prime square plus 2 v2 prime square, and 3 v1 19 is equal to 3 v1 prime plus 2 v2 prime. So then you have yourself a simultaneous equation, one linear, one quadratic. This is actually this is solvable by substitution. Yeah, so you can do substitute v1 prime in terms of v2 prime and then substitute here, and you can solve it. Yeah. So it's a bit of a lot of work here if you want to do it by hand, but you can also probably use some help with the software or computer to help you to find the solution. But it's doable. Yeah. So this is just equation. So solving equation, and we're not going to do it here, but the idea is that this is a simultaneous equation. Okay, again, write down v1 prime or v2 prime in terms of one another, and then substitute into the first equation, and it's going to be quadratic, and then you solve it. Another type of collision we can solve for in this example is that when the collision is perfectly inelastic. In other words, they move together or stick together with the same velocity. Now in this case, after collision, they will have the same velocity, so I can actually drop the subscript because they're all the same, and that they move together. So in other words, like one is attached to another, they move with the same velocity. So in this case, this become m1 p prime plus m2 phi prime, which is equal to m1 plus m2 phi prime. So this simplifies the calculation a lot. Yeah. So, but remember, this only works for perfectly inelastic collision in which the two objects stick with each other after collision. In this case, m1 plus m2 is 5. So we can set this equal to this. So this is very simple. Yeah. So phi prime would be 19 over. So they will move together with the speed of 19 over 5 meters per second to the right. Okay, so now you see this type of collision. Now for the partially elastic one, is usually obviously you cannot solve it with just conservation of momentum. So there must be other known quantity, like for instance, what is the velocity of one of the particle after collision before you can solve for the other. Yeah, and remember, in this case, just like for the perfectly inelastic one, the kinetic energy is not constant. Okay, so this concludes our discussion about momentum, impulse, and type of collision. I hope that this series of lessons about dynamics helps you understanding the core, the basic principle of dynamics, and hopefully you will be able to understand more about mechanics as a whole. Please don't forget to like, subscribe, and share the video. I'll see you in the next lesson.